Imagine, just for a second, that you are walking around right now carrying this little pouch of flesh-melting acid inside your body.
Right, just a casual pouch of acid.
Exactly. I mean, an acid so incredibly potent that it can break down a thick, tough steak in a matter of hours.
It is incredibly corrosive, yeah.
And yet, miraculously, this acid doesn't dissolve the pouch itself. It just sits there, doing its job, safely contained.
Most of the time.
Most of the time, right. But what happens when that biological containment system actually fails? Like, what happens when the pouch starts to literally digest itself?
Well, it's honestly one of the most fascinating betrayals of human physiology. When your stomach's defenses break down, the consequences are severe, and understanding how it happens means we really have to look at some incredibly complex cellular engineering.
So in this deep dive, we are exploring peptic ulcer disease, or PUD. We're going to figure out how literal holes form in your gut lining.
Yeah, the actual mechanics of how acid and bacteria dismantle the GI wall.
And we're going to get into the wild story of how a single scientist changed medical history by drinking a beaker full of pathogens.
A truly legendary moment in medicine.
Oh, absolutely. So whether you're prepping for a med school exam or you're just insanely curious about how your body works, we've custom tailored this deep dive for you.
Skipping the overwhelming jargon, but keeping all the rigorous science.
Right. But first, I feel like we need to define the actual threat here. What separates a true peptic ulcer from, say, just a standard stomachache or a bit of inflammation?
So the critical distinction really comes down to the depth criterion. I mean, an ulcer isn't just a surface scratch.
Okay, so it's deeper.
Much deeper. A true ulcer is a complete physical break in the mucosal lining of the stomach or the duodenum.
Which is the first part of the small intestine, right?
Exactly. And to actually classify as an ulcer, this break has to penetrate completely through a specific anatomical layer called the muscularis mucosae.
The muscularis mucosae. That sounds like a very definitive structural wall.
It is. It's this very thin, continuous band of smooth muscle. And it basically separates the superficial lining, the mucosa, from the deeper tissue, which is the submucosa.
So what if the damage doesn't reach that deep? Like if it just stays on the surface?
Then we call it an erosion. Erosions are shallow, and they usually heal up without leaving a trace. But a peptic ulcer breaches that muscle wall entirely.
Oh, wow.
Yeah, it extends into the deeper submucosa, and it leaves a permanent scar. And in severe untreated cases, it can erode straight into a major blood vessel.
Which sounds terrifying.
Or worse, it can perforate the entire wall of the gut, emptying your stomach contents directly into your abdominal cavity.
Which obviously becomes an immediate life-threatening emergency.
Absolutely.
So to understand how a hole of that magnitude forms, we should probably look at how the stomach avoids digesting itself on a normal day.
Yeah, the baseline defense system.
Right. Like if we picture the stomach lining as a medieval fortress, it is under relentless siege by its own defensive weapons.
That's a great way to put it.
You've got the hydrochloric acid acting as the boiling oil, right? And then this enzyme called pepsin, acting as the foot soldiers who are actively trying to dismantle proteins.
Exactly. And the fortress survives because it has this highly dynamic, multi-layered shield. First, there's a physical and chemical barrier.
The mucus, right?
Yes, a really thick layer of mucus, but it's laced with bicarbonate.
Oh, so it's not just slime.
No, the mucus actually traps the bicarbonate right against the surface of the epithelial cells.
Yeah.
So it neutralizes the acid before it ever even touches the tissue.
That is incredibly smart design.
It is. And then underneath that, the epithelial cells themselves are fused tightly together by what we call tight junctions.
To stop leaks.
Exactly. It prevents the acid from seeping through those microscopic spaces between the cells.
Okay, but what if the acid does manage to leak through? Like if those tight junctions fail?
Then the stomach relies on a secondary fallback system. There is this extremely robust microvascular blood flow directly beneath the surface.
Like a rapid response system?
Precisely. If acid back diffuses into the tissue, that blood flow delivers chemical buffers to neutralize it. And it physically whisks the toxic hydrogen ions away.
Oh, that's wild.
Plus, the entire epithelial layer completely replaces itself every few days through rapid cell turnover.
So peptic ulcer disease is fundamentally just a failure of this crazy equilibrium.
Right. And ulcer forms either when the aggressive factors just totally overwhelm these defenses or when the defenses themselves are stripped away.
Okay, let's unpack this. Because if the body has a multi-tiered defense system that constantly replaces itself, it seems like it would take an overwhelming amount of acid to actually breach the wall.
Well, you're not alone in thinking that. That was literally the foundational assumption of the medical community for a century.
Really? Just blame the acid.
Yep. In 1910, this surgeon named Carl Schwartz coined the phrase, no acid, no ulcer.
No acid, no ulcer.
Catchy.
Very kitschy.
And the dogmatic belief was that hypersecretion of acid was the sole driver of the disease.
And to be fair, there are edge cases where that is entirely true, right? Like Zollinger-Ellison syndrome.
Right, Zollinger-Ellison is the ultimate proof of Schwartz's logic. It was first described in 1955.
And that's a tumor, right?
Yeah, it occurs when a patient develops a really rare gastrin-secreting tumor, usually in the pancreas or duodenum.
And gastrin is the hormone that normally tells the stomach to pump out acid. So a tumor producing it would just jam that signal into the on position permanently.
Exactly. The stomach responds by producing massive, unregulated oceans of hydrochloric acid.
Oceans of it. Wow.
The sheer volume just completely overwhelms the mucus and the bicarbonate. Those patients develop severe multiple ulcers that just do not respond to standard treatments.
Because the tap is stuck on.
Right. It definitively proves that acid hypersecretion alone is capable of destroying the gut lining. But here's the catch.
It's rare.
Incredibly rare. About 1 in a million people per year.
Okay, so for the vast majority of patients suffering from ulcers, sheer acid volume isn't the primary villain.
Not at all.
Which brings us to this massive, century-long blunder in medical history. Because the establishment believed so fiercely in the acid-only model, they spent decades blaming the wrong culprits entirely.
It really was a huge blind spot. From the 1800s, when ulcers were called Crevalier's disease, straight into the late 20th century, ulcers were viewed as a lifestyle disease.
Wait, so they just blamed the patient's lifestyle?
Oh, completely. The consensus pointed to stress, spicy food, genetics, having an overly demanding job.
That is wild. The treatment protocols based on that assumption sound so primitive by today's standards. Like, I was reading about the sippy diet from 1915.
Oh, the sippy diet.
They had patients eating hourly meals of milk and heavy cream. I assume the goal was just to physically coat the stomach.
Yeah, to coat it and give the acid something else to digest. It was a very crude buffering strategy.
And totally ineffective in the long run.
Right, because today we treat severe acid issues with proton pump inhibitors, or PPIs, which operate on a cellular level.
Shutting down the actual pumps.
Exactly. They irreversibly bind to the HK-ATPase enzyme. That's the molecular pump on the parietal cells that literally pushes acid into the stomach.
So you turn off the tap, but the sippy diet just threw milk at the acid after it was already in the stomach.
Providing mild, temporary relief at best.
And when the heavy cream inevitably failed to heal the hole in their gut, doctors turned to surgery.
Really drastic surgery. They would perform a vagotomy, literally severing the vagus nerve to stop the brain from sending acid-stimulating signals.
Oh my God.
Or they would just amputate part of the stomach altogether.
They were subjecting patients to major life-altering surgeries just because of a deeply ingrained dogma. I mean, if we thought acid was the only issue, how did they ignore the possibility of an infection?
Well, because of another false belief. The medical community firmly believed the human stomach was completely sterile.
Because the logic was that a hydrochloric acid kills bacteria. Therefore, no bacteria can survive in the stomach, which means ulcers cannot possibly be an infectious disease. It's like this completely closed loop of reasoning.
A closed loop that remained sealed tight until the early 1980s.
Enter the rebellious scientists.
Yes, 2 Australian researchers, a pathologist named Robin Warren and an internal medicine trainee named Barry Marshall.
Okay, this is where the story gets so good.
They started looking really closely at stomach biopsies from patients with gastritis and ulcers.
And Robin Warren noticed these little curved bacteria colonizing the stomach lining on the microscope slides, right?
Right. So he brought Barry Marshall on board, and they eventually managed to culture this bacteria, which we now know as Helicobacter pylori.
Or H. pylori, for short.
Exactly. So in 1984, they submit this letter to The Lancet, suggesting that this bacteria, not stress, not diet, was the actual cause of peptic ulcers.
And the establishment just welcomed them with open arms, right?
Yeah, definitely not. The establishment rejected the idea entirely.
Because it contradicted everything they'd been taught about the sterile stomach.
Right. And animal models weren't easily replicating the disease. The broader community was just highly dismissive.
Okay, so facing this massive wall of institutional skepticism, Barry Marshall takes this extraordinary step. I love this part.
It is wild.
In 1984, he cultures a broth swarming with living H. pylori bacteria, and he just drinks it himself.
It remains one of the most famous acts of self-experimentation in modern science.
He literally drank a beaker of pathogens. And within a week, he experiences severe nausea, vomiting, halitosis.
And then an endoscopy confirmed that his stomach lining was heavily inflamed. He gave himself acute gastritis.
Which proved the H. pylori had completely colonized the tissue.
Right. And then he just took a standard course of antibiotics and cured his own infection.
Incredible. That single-subject proof of concept eventually earned Marshall and Warren the Nobel Prize in Medicine in 2005.
Well deserved. But there's a really poignant historical footnote here about how the scientific community filters information.
Oh, like what?
Back in 1958, a Greek physician named John Lykoudis actually observed in his private practice that antibacterial regimens were curing his ulcer patients.
Wait, in the 50s, he was treating people with antibiotics.
Yes, for decades. But because he couldn't isolate the specific bacteria in a laboratory setting, the major medical journals repeatedly rejected his findings.
That is tragic. So he was basically ignored until history vindicated him after he died?
Pretty much. It really highlights the tension between clinical observation and established theory. But, once we finally accepted that bacteria could survive the acid, the obvious question became how.
Right. Acid alone doesn't usually cause an ulcer, so how does this specific microorganism physically drill a hole in the gut?
So how does it survive?
Well, I like to think of H. pylori as an astronaut, right? Landing on this highly acidic, hostile planet. It has to be wearing some sort of specialized spacesuit that generates a localized, survivable atmosphere.
That's a great analogy. And the mechanism driving that spacesuit is an enzyme the bacteria produces called urease.
Urease, okay.
So the stomach naturally contains urea. H. pylori secretes urease, which breaks that urea down into ammonia and carbon dioxide.
Wait, urea splits into ammonia, and ammonia is highly alkaline.
Exactly.
So by producing ammonia, the bacteria is instantly neutralizing the hydrochloric acid right around its own cell body.
It envelops itself in this microscopic cloud of neutral pH.
That is so devious.
But surviving the acid is only the first step. It still has to reach the tissue. And gastric mucus isn't like water. It's a highly viscous gel.
So how does it move through it?
H. pylori is equipped with multiple sheathed flagella, little whip-like tails.
Like little propellers.
Right, propellers specifically adapted to move through thick environments. Furthermore, that ammonia generated by the urease actually changes the properties of the mucus.
It changes the mucus?
Yeah, it turns the thick gel into a thinner liquid, allowing the bacteria to just swim freely down to the epithelial cells and anchor itself in.
Wow. So it bypasses the physical barrier, neutralizes the chemical barrier, and anchors to the tissue.
And once it's attached, it triggers chronic inflammation. But the real damage, especially in the duodenum, comes from how the bacteria disrupts the stomach's chemical regulatory system.
Right, because there's a whole feedback loop.
Yes. In the lower part of the stomach, the antrum, there are these specialized cells called D cells. And they are responsible for producing a hormone called somatostatin.
Okay, so if gastrin is the gas pedal driving acid production, somatostatin must act as the brake pedal to keep things in check.
Exactly. When there's sufficient acid, D cells release somatostatin, telling the parietal cells to stop pumping. But an H. pylori infection in the antrum actively suppresses those D cells.
Oh, wow. So it essentially cuts the brake lines.
Totally severs them. Without somatostatin, the regulatory feedback loop is broken. Gastrin levels rise, and the parietal cells go into overdrive.
The stomach produces a massive excess of concentrated acid.
And that acid eventually spills down into the duodenum, which is simply not engineered to withstand that kind of chronic chemical assault.
And the acid burns a deep ulcer into the wall. So that explains the bacteria. It manipulates the environment and tricks the body into destroying its own tissue. But what about the second major cause?
The one that doesn't involve an invader at all.
Right. How does popping a common painkiller for a headache end up drilling a hole in my stomach?
So this pharmacological pathway is driven by NSAIDs, non-steroidal anti-inflammatory drugs.
This includes really common over-the-counter stuff, right? Aspirin, ibuprofen, naproxen.
Exactly. People take these daily for headaches, arthritis, sprained ankles. And they work by blocking an enzyme in the body called cyclooxygenase, or COX.
Which halts the production of inflammatory chemicals and reduces pain.
Right. But the issue is that the COX enzyme comes in different forms. By blocking COX-1, you reduce inflammation, yes, but COX-1 has a vital baseline function in the stomach.
Oh, I see where this is going.
It is required to synthesize molecules called prostaglandins.
And if I recall, prostaglandins are the specific molecules that tell the stomach to maintain that protective mucus layer, right?
Yeah.
And keep the mucosal blood flow running.
Exactly. If you inhibit COX-1, you systematically shut down the production of prostaglandins.
So mucus drops, bicarbonate halts, and blood flow decreases.
You are stripping away the fortress's shield entirely. Once those defenses are down, even normal baseline levels of stomach acid will begin to erode the vulnerable tissue.
Wow. So if you're taking ibuprofen every day for a bad knee, you aren't just irritating your stomach, you are chemically disabling its ability to protect itself.
And this creates a very dangerous clinical scenario. Because think about the nature of the drug.
It's a painkiller.
Right. NSAIDs blunt pain signaling. So an older adult taking chronic NSAIDs for joint pain might be developing a massive deep ulcer that is eroding straight into a blood vessel.
But they don't feel it.
Because the drug is masking the pain, they don't feel that classic burning sensation in their abdomen at all.
So they have zero warning.
The very first sign of a problem might be when they show up to the emergency room with severe anemia, black tarry stools, or just a massive gastrointestinal hemorrhage.
A silent bleed. That is terrifying. But medical science tried to solve this problem, didn't they? By targeting the enzymes more specifically.
They did. Pharmaceutical companies developed selective COX-2 inhibitors.
Because COX-1 is the stomach protector and COX-2 is the pain driver.
Exactly. The theory was elegant. Drugs like rofecoxib, better known as Viax, were engineered to block only COX-2, leaving the stomach-protecting COX-1 completely alone.
It sounds like the perfect solution. Keep the shields up, stop the knee pain.
It successfully reduced GI bleeding, for sure, but it introduced a devastating cardiovascular trade-off.
Wait, how does it affect the heart?
Well, the vascular endothelium relies on COX-2 to produce prostacyclin, which keeps blood vessels dilated and stops platelets from clumping.
Okay.
But meanwhile, the platelets themselves use the uninhibited COX-1 to make thromboxane, which actively promotes clotting.
Oh. I see the imbalance. If you block COX-2, you lose the anti-clotting factor, but because COX-1 is still running freely, you're still producing the pro-clotting factor.
The blood becomes hypercoagulable. Patients on Viax started developing blood clots, leading to a huge increase in heart attacks and strokes.
Which is why it was pulled from the market.
Dramatically withdrawn in 2004. It's a very stark reminder of how delicately balanced these biochemical pathways really are.
So what does this all mean for you, the listener? Because these two primary causes, the bacteria and the painkillers, are fundamentally altering the stomach's baseline chemistry, it makes sense that just patching the physical hole wouldn't actually solve the problem.
Not long-term, no. Healing the ulcer symptomatically is insufficient if you don't eliminate the root cause.
Right.
I mean, if a patient takes an acid suppressor, sure, the ulcer will likely heal. But if H. pylori remains anchored in the tissue, the chronic inflammation persists.
And chronic inflammation is never good.
Over decades, that continuous inflammatory state damages the host DNA and alters cellular turnover. The World Health Organization actually classifies H. pylori as a Group 1 carcinogen.
A Group 1 carcinogen, meaning there is definitive evidence it causes cancer, specifically gastric adenocarcinoma.
Yes. But the bacteria is also linked to another fascinating malignancy called gastric multilymphoma. Mucosa-associated lymphoid tissue. It's a type of cancer where malignant V cells accumulate in the stomach lining.
But the way doctors treat this specific lymphoma is incredibly unique, isn't it?
It is honestly one of the most remarkable phenomena in oncology. In early-stage gastric multilymphoma, the malignant B cells are often still dependent on signaling from T cells to survive and proliferate.
Okay.
And those T cells are only active because they are constantly responding to the presence of H. pylori.
Wait, so the cancer is relying on the immune system's reaction to the bacteria?
Yes.
Which means if you kill the bacteria...
The T cells stand down, they stop sending the inflammatory growth signals, and without those signals, the lymphoma cells literally starve and undergo apoptosis.
They just die off.
By administering a combination of powerful acid suppressors and targeted antibiotics to eradicate the H. pylori, the cancer itself can regress and completely disappear.
It is a cancer that can frequently be cured by treating a bacterial infection. That is an astonishing biological mechanism.
It really is.
But I want to clear something up here. If this bacteria causes deep ulcers and drives certain cancers, is a completely sterile stomach the ultimate goal for health?
Oh, not at all. Actually, a massive percentage of the global population harbors H. pylori in their stomach.
Really?
Yeah, often acquiring it in childhood. And the vast majority will never develop an ulcer, let alone cancer. The presence of the bacteria is necessary for the disease, but it's not sufficient on its own.
So why does it peacefully coexist in some people, but cause massive tissue destruction in others?
Well, it requires a perfect storm. It depends on the host's genetic susceptibility, environmental cofactors like smoking, and the specific strain of the bacteria.
Because some strains are worse than others?
Exactly. Some strains carry severe virulence factors, like the KG gene. Strains with this gene actually inject a specialized protein directly into the host's epithelial cells, which massively disrupts cellular function and heavily amplifies the inflammatory response. So it's definitely not a simple equation of bacteria equals ulcer.
That makes a lot of sense. And we should probably put to rest the oldest myth in gastroenterology while we're at it: spicy food and stress.
Oh yes, we can confidently say they do not cause peptic ulcers.
The final nail in the coffin for that myth.
Right. Now, if you already have a breached mucosa, eating a highly acidic or spicy meal or experiencing severe physiological stress can certainly aggravate the exposed tissue.
It'll hurt, sure.
It'll make the pain worse and impede healing. But they are not the primary culprits initiating the mucosal damage. That blame rests squarely on H. pylori, NSAIDs, and a few rare idiopathic cases.
Idiopathic meaning we just don't know the cause.
Right.
So to pull all of this together, we've looked at how a true ulcer isn't just a scratch, but a breach of the muscularis mucosa.
The structural wall, yeah.
And how the stomach's defenses rely on this beautiful, delicate balance of mucus, bicarbonate, and blood flow.
The fortress defenses.
Exactly. We explored how painkillers systematically disable those defenses by blocking prostaglandins, leaving older adults vulnerable to silent bleeds.
A huge clinical issue.
And we saw how H. pylori uses urese to neutralize acid and specialized flagella to swim through the mucus, ultimately cutting the stomach's regulatory brake lines.
Right. Zooming out, this is just a really significant public health narrative. H. pylori infections are closely tied to global sanitation, crowded living conditions, and poverty.
While NSAI ulcers plague our aging population.
Exactly. But fundamentally, I think the history of peptic ulcer disease is a masterclass in medical epistemology.
A cautionary tale about how slowly prestigious institutions update their beliefs, even when staring direct evidence in the face.
For a century, the global medical establishment clung to the stress and acid model. They subjected patients to totally ineffective diets and severe nerve-cutting surgeries.
Just actively rejecting evidence that contradicted their preconceived notions about the stomach being sterile.
It took incredible persistence and Barry Marshall's willingness to literally infect himself to finally force the establishment to look at the data objectively.
Which leaves you, the listener, with a final lingering question to mull over. If the smartest medical minds in the world were confidently wrong for 100 years, treating infectious wounds with heavy cream and surgery simply because they couldn't imagine a bacteria adapting to stomach acid, what other established foundational facts about our bodies are we completely blind to right now, just waiting for the next rebel researcher to drink the petri dish and prove us all wrong?